Welcome back, students. In the previous video, we went through 5.1 random variables along with some review of chapter 4. Now let us begin 5.2 probability distributions. Here's a hard question. What is so-called a probability distribution? Well, here's an answer by our textbook authors, or an attempted answer here in this box, page 233. Probability distribution, a distribution of the probabilities associated with each of the values of a random variable, and so on. I don't know about you, but I didn't understand a thing what was written here. I mean, they're trying to explain what is so-called probability distribution with a phrase like a distribution of the probabilities. They just changed the order, and all of a sudden we are supposed to be able to understand it, along with some further jargons that are unclear. I mean, this is crazy. This is almost the worst, quite possibly the worst explanation I have ever seen anywhere. Well, but I'm not really about to blame our textbook authors, because I know for a fact it is an impossible task. I mean, should I do something like this? A distribution is a dual linear functional defined on a set of infinitely differentiable functions with a complex support and some further properties that we discussed in the previous chapter. We get probability distribution. This is almost as crazy. I don't think anybody understood it, so why would anybody bother? That's my take here. Instead of trying to define or describe probability distribution, I'm going to distort it a little bit for the purpose of this class. This is what I'm going to do. I'm going to define two very concrete concepts. I didn't say easy, I said concrete. Probability mass function, number one. Cumulative distribution function, number two. These two. And we are going to study some examples of those. Many examples, actually. They're going to be challenging. Now, this is my approach on probability distribution for this course. A probability distribution of a discrete random variable is its probability mass function and the cumulative distribution function put together. This is not widely accepted notion of probability distribution, but at least this way some people can understand. I mean, probability mass function, yeah, this is not easy, but we're going to go through many examples, so you should be able to understand it. This one is going to be a bit harder, but you have to learn these. And these two put together will be the probability distribution. As far as my course is concerned, that's what I'm going to do. Okay, let's begin the first one, the probability mass function. It is defined kind of like this. It's a real function, so small x is a real number, and p of x is also a real number. And how is it defined? The probability that the random variable x takes that small x value. There are two x's, so that can be a bit confusing. Random variable is capital X. Small x is the variable here, so they are related, but they are not the same. Well, if it'll be too confusing, doing some examples will help. So let's go over to this example here, example 3.3. It's the same example we studied before in the previous section. We have an urn model with 10 balls, 5 red, 3 green, and 2 blue balls, and also I just color-coded RGB. And then we created these 3 random variables. And let's define a mass function. Okay, mass function of the first random variable, let's find out. And let me show you the answer. It should be like this. Let's see. Let me get this definition of the random variable. Excuse me, the definition of this mass function down here so that we get everything in the same viewing window. Alright, Okay. Now let's look at this random variable capital X. That capital X can take three numerical values. X equals to 0, capital X equals to 0 when you get the red ball, capital X equals to 2 when you get the green ball, capital X equals to 3 when you get the blue ball. These are three possible values of this random variable capital X. And how is the probability mass function defined? It is defined as the probability that this random variable take. So this capital X can be these three values. In these three cases we have probabilities. Otherwise, impossible. They're all zeros. That's what we see over here as a mass function. When small x is equal to 0, which means the capital X takes 0. That corresponds to the red ball. When small x is 2, that means the capital X takes the value 2. That corresponds to the green ball. So the probability is 1/3. When capital X is, when small x is 3, that means capital X takes value 3. That corresponds to the blue ball. So the probability is 2/10. So we have 1/5. Otherwise, impossible. So otherwise the probability is all 0 because it is impossible to get anything else. That is the mass function here. By the way, here is a graph of that mass function. When x equal to 0, we have this red dot, which means that's a y-coded value. That's a probability, 0.5. When x equal to 2, we have green ball, so 0.3. That's a probability. When x equal to 3, then 0.2. 1/5, that's a probability. Otherwise, the probability is all 0, as you can see down here. That is a graph, typical graph of the mass function. Bunch of dots. Now, this can be tricky, so let's do this multiple times. Let's use this time the second random variable, and let's define our mass function. Oh, let's change this definition too appropriately. I should have done that in a previous example too. Let's do it like this, because the random variable is now capital Y, and then that mass function is given as g of x. Okay, according to this definition, capital Y can take three numerical values: -1.5, which corresponds to the red ball, 0.5, which corresponds to the green ball, and 1, that's when you have the blue ball. Otherwise, impossible. So probability is all 0. So how do you get the mass function? When small x is -1.5, the probability of red. When small x is 0.5, the probability of green. When small x is 1, again you need the probability for that case, probability of blue. Otherwise, all 0. Here we go. When x equals to -1.5, small x is -1.5, that means this capital Y is taking that value, and that corresponds to the red ball. So we have the probability of 5/10, 1/2. When x value is, small x value is 0.5, in this case, capital Y takes 0.5, and that corresponds to the green ball. There are 3 green balls out of 10, so the probability is 3/10. Finally, actually next to finally, when small x is equal to 1, capital Y is taking value 1, that corresponds to the blue ball, so the probability is 1/5, because there are 2 blue balls out of total 10. Otherwise, impossible, so all 0. Here's a graph. bunch of dots, and then otherwise all 0. -1.5, x equals to -1.5. In that case, we have that probability 1/2. X equals to 0.5, we have that probability 0.3. X equals to 1, we have that probability 0.2. Otherwise, all 0. Okay, we have enough time for another exercise. Hopefully, 2 exercises we just went through will help you doing this one. Alright, let's consider the third random variable here, z. So let's define this math function h of x as probability where capital Z takes the value x. And what are the possible values of x? -1.25 or 4.75. Otherwise impossible. So you have, well, 3 cases: -1.25 case, 4.75 case, otherwise. When x equals to -1.25, you have either red or green, so that probability is 0.8. Yes, there are 8 such balls. And when x is 4.75, what's the probability that z takes that value? You have to have blue balls, so that probability is 0.2. Otherwise, all 0. Well, here we go. This is red or green. This one is blue. Otherwise, all 0. And here is the graph of the mass function. X equals -1.25. Okay, here's that probability. X equals to 4.75. Here is that probability. Otherwise, all 0. Okay, we have a little bit of time left. We're going to talk about cumulative distribution function in the next video, but let's take a little bit of time to explain it. Let's see. Mass function is defined kind of like this. Probability that this random variable takes that particular value. Cumulative distribution function is the probability that the random variable takes that value or less. So everything that happened before up to x is all cumulatively included. So x goes bigger, that means more accumulation. So instead of, unlike probability mass function, this cumulative distribution function should be increasing. Exactly how will they look like? Let's discuss that in the next video.